What's changing in the interface IP market?
So one of the major things we see in the interface IP market is that SoCs need to take in more and more data. They want to connect big hard drives, and they want to be able to access them very quickly. They want to, connect to high-speed cameras, HD video. So SoCs need to access a lot more data than they needed to a few years back. And the cheapest way to do that is turning out to be to increase the speed of the interface and go from a few hundred megabits to a few gigabits per second. And the main challenge in doing that we see is, first, even though the interface speed is going up, the power budget is not actually increasing because devices are going mobile and they're portable. So you want to stay within the same power budgets, in many cases going down, but at the same time increase your speed. And the second thing, the big challenge, which is making this problem difficult, is as people go to the more advanced node, as you go from 90 to 65 to the 40s to 28 now, the design rules are becoming more and more restrictive. So these two issues, which is increasing speeds with constant power budgets and more complex and more limiting DRC rules, are creating big challenges to actually get to higher speeds.
So basically the designers are caught right in the middle here. They have to work on both sides at the same time, right?
That's right. And what we are trying to do at Viraj is we are trying to build the IP so that we can allow people to meet the need, the ubiquitous need for high-speed interfaces that is there throughout the market. So we are building, we have a specialized team that is focused on it. We understand the technology very, very well, so we can build the solutions. And our goal is to provide the best technology at the lowest risk. So you can integrate and get access and meet the requirements of this very challenging market.
The restrictive design rules, do they start easing up as we move into the next node, or even into more when 28 nanometers becomes more mainstream and more tested?
No, it doesn't. So what happens is, as you go down to the next node, the design rules get even more restrictive because the foundries have more limited design rules to allow them to get better yields and to reduce their own costs of masks and manufacturing. So as you go from each node to node, you have to actually change your IP quite a bit. And if you want to meet the high speed with good yields and able to go to production with millions of units, you need a lot of specialized expertise. That's what we focus on. That's what we build.
Power is an interesting area here because as we start pushing down, everything starts taking more power. You require more speed, more power, and yet everybody's being forced to do it with less. Is it just a simple matter of now we have to start putting in lots more techniques like clock gating, high K metal gate, or is there even more complex than that? Does it have to be built right into the IP?
Now, it has to be, it's very integral to the IP architecture because the simplest way to get higher speeds is to spend a lot more power. Just have higher currents all the way through, and everything will switch faster, and everything will move faster. But that is exactly the wrong thing to do. So you want to minimize the currents you use. But at the same time, these advanced nodes and advanced processes have much greater variation in the process, much greater OC weight. So you need on-chip calibration. Sometimes you need it one time. Sometimes you need it to be continuous. So a lot of advanced technology is required to actually allow you to keep your power down while being able to meet the high speeds across wide variations in the process and operating conditions.
The way that a lot of SoC vendors have managed to do both is by increasing the frequency while also dropping the voltage. But what that does, and what it's starting to do, is increase the leakage while at the same time adding to things like signal integrity problems. How do you manage those two?
So, those are the problems that we see. And there's no simple magic bullet that will actually answer and meet all the requirements. So again, where it comes back to is the team that does the IP has to have a lot of knowledge about how do you actually get the higher speed without taking the easy way out, which is, hey, just dissipate more power. So there's no easy answer, and it just is very challenging to actually meet the requirements.
Are on the other side, are the teams that are building the SoC and designing it and creating the architecture in the first place, are they doing the hard stuff, such as the multiple power islands, the clock gating, or are they still trying to say, okay, we can try and do this at an older node, or we can try and fudge it somehow?
What we see is that most of the people who want the higher speeds, the higher performance, they want to go to the advanced nodes because the advanced node gives you smaller die sizes, gives you lower costs, right? So it helps them compete in the consumer markets. So you are forced to go to the higher nodes, and all the SoC designers, they actually are using advanced techniques like power, the clock gating, multiple voltage islands. The IP that we build has to be able to fit in with that architecture. So that is part of the design that we do, which comes in from the beginning.
As we go forward, even beyond 28 into 22, what happens then? What's the vision looking down the pike?
So we see some big transitions as we go down the process. When we went from 65 to 40, we saw some major changes happening. From 40 to 28, there are changes, but they're not as significant as a transition to 40. So going 22, we are already planning for that transition. So the architecture we do, the designs that we are doing, are being done keeping in mind that we will need to move 22 in the near future. So we don't expect big challenges, and we expect the IP to be able to easily migrate to those nodes.
Ragha Vanmenon, thank you very much.
Okay, thank you.